Can you get help in projecting things from screen to here? Okay.
I think probably would kind of kick automatically if people were video, but I can go change for that.
It's some of you are already exposed to this. It's a favorite part of the class. Okay, well, thanks much for this. So probably you know why your free view here is a required class, right? Who would come to this class without requirement? Anyone would consider coming in here without requirement? Okay, at least one halfway lifted hand and one it depends. Well, I would teach this class even if not required. So who needs physical chemistry? Yes, I understand, but who needs physical chemistry philosophically, generally? Why it is needed? Why you cannot be happy chemist just by mixing some pure odorless or with fragrances? Okay. What's the reason of this subject? What's a part of this building block in the whole building? Yeah, understanding internal structure, and this is more academic point of view, like just to grow intellectually, and if you go to research development, teaching, or academia, you can like make theories and success. But if you are looking for more applied problems, if you don't care about mechanisms and structures, if you like real industry, what is in what everyone may need? You don't need to answer out loud if you're not sure, but try to develop answer in yourself. And by the way, I'm very happy that you are some of you taking notes. It's really critical. Without taking detailed notes, it can be harder. So I applaud your effort. And I will give sign if something is really important. To record. So you do not need to believe me in anything. I do not have any degree in chemistry. All my degrees are in physics, but I was hired to a different chemical department for a period of time and got over it. So the chemistry has two major branches: synthesis, fabrication, and characterization. And for major part of the organic chemistry is synthesis, fabrication, and inorganic is also mostly synthesis. Biochemistry is very aside. But analytical and physical are much more targeted towards characterization. So if you already have some substances, some molecules, you can characterize their properties like color, density, odor, and stuff. And mechanisms of reactions. So if we want, right now, this course will be very academic. Next semester there will be PCHEM lab with more, not visible, with more practical things like how to measure spectra or mass spectra of some things. But we are developing background for characterizing chemicals. And of course, your idea about understanding how things work. Good. So where did you stop last time? We all made the record that it was a bad connection.
Standing. Yeah, green slide.
Yeah, thank you, thank you. We will get there. So the molecules consist of atoms, and atoms consist of positive nuclei and negative electrons, and mu can be and if previous year is posted on YouTube, have this link so you can listen to it, and I will try to record and give it to you if you, some of you, if you do not like to read your own notes. Yeah, so the problem is, there is no problem with nuclei. If you are taking physics in your high school, give raise hands if you didn't. You didn't. So only two didn't take physics in high school. The rest, you are my heroes. It's a right audience. It was good selection to go to PCHEM. So you know that there is Newton equation that like if you have some balls with velocities, they will propagate somewhere. So same for nuclei, positive charged nucleus. No problems. There are equations that humankind knows how to solve. But with electrons, now we do know. Well, some of us know, and we all will know by the end of the course. But like 100 years ago, even less than 100 years ago, no one knew how electrons are moving. You know from your general chemistry background, high school chemistry background, is s, p, d orbitals, that they're like ears of bunny or petals of a flower. So one electron, and it has so many features. So it behaves like a wave, like a distribution space. And our narrow goal for this course is to absorb the laws of nature that make electron to distribute this way in space. On one hand, and how this distribution space will propagate on the other hand. And if you look more generally, how to get properties of your molecules out of this ears of bunnies, this distribution space. Okay? So, and we are investing a little of time at the beginning, generally to the concept of wave. So it is an object, like if you have wave of any nature, if you have one like ball, table, whatever, beaker, you can put position space, maybe some twist angle, and that's it, right? And if you have a wave, you need to point out how high it is at any point of space. It's like distribution, many degrees of freedom. It is a true challenge for math. It's a much complicated than just Newtonian motion. What's the easiest object that obeys wave nature and can be understood by human intuition? Huh? Sound? Yes. Yes, I hear your sound. We can understand it. What else?
Water.
Huh?
Light.
Yes, okay, but it's maybe not as simple.
Water.
Waves on the surface of water. What else? They all are either three-dimensional as sound or two-dimensional as water. Is there something simpler? Who plays music? Which instruments do you play?
Yeah.
Cello?
Yeah.
French horn.
French horn?
Yeah.
Okay, same as Prince Louis de Broglie, who is one of the developers of quantum theory, because inside the trombone there is a sound wave, but on the strings of cello and piano, you know, there are waves, and there is a main harmonic when the whole string elongates, and there are harmonics when one half goes up, another is down, like overtones, if you are right. So this is the mathematical description of a string was a great challenge to humankind, to scientific society at the time of French Revolution. And mathematical equations were developed at this time. But then it took about 100 years more to bring it over to electromagnetic waves, to quantized electrons. Standing waves. If you multiply two waves that are running into each other, you get nodes and volts, right? So this stuff will stand and this will oscillate, right? And you have separation of space and time parts. So space part is one cosine, time part is another cosine. And they are kind of independent. I better write it down, otherwise really quickly skim through slides, but I have a great fear that neither you nor myself will remember what was it. So I better slow down and do some scratches on the screen. So even if you sacrifice time. So we do need a little math experiment number 2. It's underwriting. Suppose we have some functional form, some mathematical function for a wave. But we know that it's very partial. It is very specific example. It's not genuine. How mathematicians are thinking? Is there anyone who wants now? Then we are on the same boat. So they are much less practical, and the mathematical thinking goes not in having something intense, but just postulating general features without any specifics. So same about waves. If we would be mathematicians, we would say, no matter what is the function, it is important which equation generates this function as a solution. So I'm not a mathematician. I'm not inviting you to become one, but we need to borrow a little of this thing. So we need an equation that will generate this either running or standing wave as a solution. And it was a big challenge for humankind science. We will not do derivations. We'll do more like little show how it comes. So we do have there's a product of time part and space part, and each of them are assigned with this wavelength and period. And the experiment will be to take derivatives of this function. So since the function depends on position and on time, we may want to take derivatives over position and time. And since you all are so skilled in calculus and derivatives, you may go up to second derivative in each, in space and time. So you may listen how I mumble, or you can just practice on your notes. Just take this product of cosines and take off the overall function. First derivative, second. And I'll try to do the same. Your brains are brighter and you will do it quickly. I'm sure. We will speed up, otherwise I would invite someone to. So, so it's derivative for time component, and the space component stays unchanged. So this derivative of sine capital times x capital part, which is not changed. What is the cosine of the order? Not cosine of the derivative. What is derivative of cosine? Yes, perfect. I'm a little behind my own schedule, but I do have good intentions to print little summary of major equations and distribute, but maybe it will take me time. So here, prime. Derivative of cosine is negative sine, but negative sine of times derivative of the argument, right? T. 2y over t capital will come to the front, right? No one objects. Okay. So it was first derivative. Success. Now let's take the second derivative. D second So we yet keep the spatial part unchanged. So we just apply this prime symbol derivative to this first. Prime here. So, and what is the derivative of sine? Cosine with plus, right? So we keep the negative, and then we have this 2 pi divided by t squared, because each time you take derivative, the factors in front of our independent variable float to the front, right? No one is surprised by this. With hands, I will be happy to talk about this thing. Better of sequencing golden. So minus 2 pi t squared, and then we get back to cosine 2 pi t over t. What a great surprise. If you take second derivative of multiplied by x, right? So, and let me change colors. And this boxed part is nothing but our original psi. So if you take second derivative over time of our wave, we get this wave function back. It is reproduced times some prosthetic factor. If you do the same experiment, numerical experiment with derivatives over space, it will be the same result. Taken second derivative of wave function reproduces it back times some factors. Okay? I was practicing at home many years ago. So it is our experiment when we did about time. And if you do the same about space, you do the same way. So now, by taking derivatives, we do not change the function. We only accumulate factors. And if you take second derivative over time and over space, we get the function back. Mathematically, no one forbids us to make equivalence, equal sign between these two second derivatives. And we need to make little tricks to take care about factors. So 2 pi squared is cancelled, and t squared and wavelength squared are left in there. Right? And by the way, what will we get divide wavelengths times divide by period?
Velocity.
Yes. Correct. And it is natural thinking, like distance divided by time, it is velocity. Velocity of who? Of what? Of wave, yes. If this wave is traveling, then it will be velocity with which it travels. So if we take care of these factors, it will be velocity here. So derivative of wave function over space, second derivative, and derivative of wave function over time equal itself. And by solving this equation, which I hope I do not have to do, or computers will do it for me, or you will do it as a homework. I'm not going to solve it, but as much as I can. But solving mathematically this equation, one will get either traveling or standing wave. Mathematical equation for a wave. Good? Are you good? You got substantial leap in your course. You know the wave equation. So second derivative over time and over space of unknown function is the wave equation. For acoustic waves, sound, for strings, drums, and for electromagnetic wave, it will be very this type of equation, mathematical equation. For electron, there will be specifics, there will be difference, but overall idea is the same. Any questions at this point? Any objections? Send email if you are hesitant to say your objections or suggestions out loud. 24 minutes. We are done with lecture mode. Now we are doing lecture based material. Who can build TV? Okay, with hands if you cannot build TV. Good, good. We are not engineers, right? It's nothing wrong with it. Did you ever seen TVs that are not flat screen? Yeah. How does it work? Any idea? Yeah. What? Perfect. But what is scanning through?
Like pass all the way to.
You guys can teach this course without me. I'll just assign shares. 12 people, 40 lectures, about 3 lectures each. And I will just watch it through online. Good. So, here is my perfect artistic drawing of this cathode, whatever, vacuum tube. So, if you create vacuum in glass tube, right, and if you create high voltage electrodes, positive and negative, direct current, not alternating, then the electrons are emitting from negative to positive, and they accelerate so much if the voltage is strong enough that they will accelerate that they will pass through the electron. And this construction is called electron gun. Now, if there are ways to deviate it in different directions. Let's forget about it. It's not a TV, it's only electron gun. And then if we do not have any screen on, one deposits zinc sulfide or any other components that will emit light upon being injected high energy electrons. And this is called scintillations. So if there is no screen, there will be flash in the middle. If you put not transparent screen and make 2 holes, one would expect that if it emits with some dispersion in different directions, then there will be like geometric optics, straight line and a little flashes here and there, right? No cheating from my side, all good, right? 2 points where it will flash. And this experiment has been done, of course, before making mass production of TVs. One did try what happens. So what happens that there appear flashes in the middle. For sure, I guarantee. They are less intense, but they do appear. And the nature, the reason for these flashes, that you cannot think about electron as like little yellow ball that goes on a straight trajectory. It's more like a wave that takes these shapes and it goes simultaneously in several directions. And those little fractions that go in this direction meet each other and create a flash. So there are more other experiments that prove wave nature of electron. I just like this one this year. But we need wave equation for electrons. And the whole course, building, solving, and finding applications for wave equation for electrons. Whew. This image was done by one of the students in this course. Not the sound. So what do you see? Describe. I can play it once again. By the end of the course, you'll be able to make this easily. So it's some uneven wheels rolling, right? So who never heard the last name Bohr, or who never heard about Bohr model? Okay, then lift hands who have heard about Bohr model. I'm in presence of highly educated people. You all will succeed. So, you know, positive ion, negative electron moves around. It was first model of an atom. And the Bohr model that not any arbitrary velocity is allowed for this planetary circular electron, but only preferred, favored, selected velocities, right? And they are quantized. Like it is in our regular life, we have traffic signs that tell no quicker than 80 miles per hour. And quantum traffic, let's say, you can ride only 80 or 90, but you cannot ride in between. It's discrete permitted velocities. And the background for this Bohr model that at this time they didn't have theory, but they have like intuitive vision that electron is wave of something, and the wave should be standing wave. So it can exist only if the amplitude of a wave at the beginning and at the end, if it is a circular wave, will match each other, will have the same amplitude. So this image is, I thought I'm taller. So this is zero line, and going green stuff going down inwards or outwards, it is amplitude of a wave. So this is one amplitude positive, and here negative. So if after making a full cycle, it comes to the same height, then it is permitted, right? And then one can have several waves, several harmonics. First, or second, somehow skipped, third, fifth. So the larger number of these nodes and lobes on the circle, the higher angular momentum. Like this would be P, and this would be 0 will be S, 2 will be T, and 3 will be F electron. Very rough. Bohr is not correct. It is just rough introduction into theory of atoms. Make sense? You saw these pictures in textbooks, right? And they are moving in time and playing sound because everything is moving. We need to look how things are changing in time. So, a little proof. Right now, we are not going into details. But what if the velocity of this wave, if the number of nodes is set up in such way that the end will not match the beginning? If someone will ask what people are doing in PCHEM class, until people are doing movies with sun. You will do it though. And by the way, some of you did return these booklets to my mailbox. You shouldn't do it, it's for you. You can come and pick it back. So if there are good waves, they will have this nodes and lobes. And if there are bad waves, they will be ugly and with a lot of noise. And you know, correct solutions are always beautiful. If something is ugly, it doesn't exist. It's basic argument. Why electrons have this SPD and do not have like P and half? It would be ugly stuff. But you can try what it looks like. So what is in the Bohr model? You have memories about, like instead of velocity, they tell about momentum, right? Which is mass times velocity. And then one goes into angular momentum, which is momentum times distance from center, right? And this stuff is quantized, is taken as a integer times Planck constant. Good? So right now I am in front of very big challenge. We could just postulate equations, wave equation for electron, but forget about course. Do you read science fiction? Who doesn't read science fiction? Okay, so most of you do. Did you Isaac Asimov? You know, like there is iPhone and there was iRobot, not the cleaning vacuum, but iRobot set of stories like half century ago. And this author has, I think this author has a short story, Day of Knowledge. When like at the beginning of year, every young people and kids are going to school only for 1 hour. Then they are put helmet with wires, and after half an hour, you get the yearly course. And then you just have fun the rest of the year. Then when it's time for next grade, you come from the beginning of the school year, and you are recorded all knowledge that you have to do. And then one of the characters of the story wanted to like be a pilot of a spaceship, but when it was time for entrance exams for a profession, he failed. And he said, what can I do? How can I trick the system? And he suddenly found that in addition to this mainstream of brainwashing reporting, there is a very little set of people who sit in libraries and really read stuff. And he started and succeeded his goal. So if you do not want to have brainwash recorded main equations, but be able to operate and navigate in space of knowledge, I need to step back and give some additional background information, which will likely not be asked from you on any exams or in next courses, but it may help you to feel more confident and have more fundamentals and background. So generally, if I would be sitting on your side, I would ask myself, okay, waves, but waves of what? What is performing wave motion for electrons? One thing. And another, what, again, same question, what is oscillating? Why is oscillating to positive and negative? Why we have this limits to number of nodes? And now I'm going very, very far. Really far. You can choose. You all know Newton's equation of motion. Okay? Give me a little sign if you're hesitant to admit it in public if you are not confident in Newton's equation of motion. Okay, so most of you are. So Newton's equation of motion is for like material points, for little balls. And you have just velocity, position, and you know how to propagate it in time. This is correct. But Newton was not alone. There were alternative ways how to predict motion of these little balls, material points. And one of them was Lagrange. So it is all time about Great French Revolution, when a lot of mathematical developments were done for civilization. And Lagrange, he was advanced mathematician, and therefore we may hate him, but his main finding based on his approach will be very near and dear. He postulated principle of least action, which intuitively the least action is something that we like. active passive. Oh, by the way, this is Newton equation, right? Second derivative of coordinate, which is acceleration, equals force divided by mass. And if there are more than one particles, more than 1 degrees of freedom, it's just same equation for each. So, what we do this time? So you need to look about at 11:50, right? When physicists who deal with mechanics, just mechanical motion, tell that their goals are successfully completed, what is the goal of mechanics? Internal mechanics. If you know the Newton equation of motion, you know what comes out of this equation. And generally, even without any physics, you can project, right? Law of motion, how position changes in time. You can give trajectories for ions inside molecules, or for ions in molecules that do collide before the reaction. Trajectories. And in oversimplified way, trajectory is position. That's right. So it oscillates or departs somewhere. And trajectory comes out of solution of Newtonian equation of motion. Right? Good. But the trajectory can be obtained from different mathematical construction, from different set of equations. And later on, we will find that this philosophical background for this additional set of equations will be extremely helpful for everything we do. So I'm taking, it's not a shortcut, it is a longer bypass, but later on you will feel happier. So how do you deal with trajectory in Newtonian mechanics? How do you deal with physics if you have little balls? You always start with writing down formulas for energy, right? For kinetic, for energy which is composed of kinetic and potential. Aren't you? Sure, everyone comes home after a long day and says, oh, okay, what is kinetic energy? Let me write that formula. So, and what is kinetic energy? What is which of these equations on the board correspond to kinetic energy? Let's be quick and simple. You wrong.
Oh, on T.
Great, thank you. So kinetic means something is moving, so it depends on velocity, and the derivative of position over time is velocity. So velocity squared times mass is T, kinetic energy. Now, which energy is symbolized by term U? Huh?
Potential.
Yes, potential energy. So potential energy, this is not general. It is an example for like spring, mass on a spring, when it is harmonic, proportional to elongation from equilibrium. But generally, potential energy depends is a simple function of coordinate. If we are speaking about like potential of electrons in the attractive force of nuclei, it is 1 over r, right? If it is some van der Waals, it is a more complicated shape. Potential energy, how energy depends on position. And now, if you add together kinetic plus potential energy, it will be function energy, total energy, Hamiltonian, which will be used in every branch of science, including the Newtonian mechanics. Lagrange was crazy. He thought, why should we add kinetic and potential. Let's subtract. I'm a mathematician. Everything is allowed for me. So if you add energy together, it is H, Hamiltonian total energy. If you subtract, it is Lagrangian. There is no correspondence in real life. It's just mathematical abstraction. And then this crazy man thought like, okay, let's do this Lagrangian, which probably depends on position, velocity. And one can integrate the value of this Lagrangian along the trajectory. Take W, multiply by increment of time, and get the S function. Do not develop internal protest. It will never be part of any exam. It's on the background. It's a little less. So this S function developed as integral of Lagrangian is known action. And there are theorems that any object in the world is lazy, mathematically. Any object in the world will perform motion in such way to have this S function minimum, as minimal as possible. So you can just suggest several trajectories by random numbers, compute action function for them, and then the one that will give least action will really exist in nature. It's a little crazy way to predict things, but it works. Whew. And if you convert this principle of least action into differential equation, it will be a Lagrangian equation, which is replacement of Newton equation of motion. Whew. I'm going to return back to more natural stream of narration. There is not. I have distributed the slides, and there is nothing new. It was on the previous one. What is the dimension of angular momentum that is quantized in Bohr model? This question is kind of disconnected, but you will see connection to everything we are telling immediately. You know, dimension is like distance times or divided by time multiplied by mass. So what is the dimension of the angular momentum?
It's like the momentum times like the distance from.
Yes, right. And momentum is velocity times mass, and velocity is distance divided by time. So this is velocity, distance times time. This is mass, and this is distance. So if you combine all together, will be distance squared times mass. And we can, you know, mathematical trick. If you multiply and divide by the same factor, nothing changes. Divide by time and multiply by time. And then one can recognize, I know you probably are tired and do not absorb any new information anymore. But if you look, distance squared times squared, it's like second derivative. It's like velocity squared times mass. mv squared, it's like kinetic energy, times time. So the dimensions of angular momentum and dimensions of action, energy times time, are the same. I don't know how to introduce it better, and I'm going to scroll back. So dimension of Lagrangian is energy, and dimension of action is energy times time, right? So dimension of action is energy times time. And dimension of the angular momentum is also energy times time. They are objects of the same nature, of the same dimension.
Could you say that one more time?
Yes. Angular momentum is important part of Bohr model. on one hand. Action is important part of theoretical mechanics. By coincidence, both angular momentum and action do have the same dimension. This is a big prompt for us to develop actual equation for electron. So probably we will be out of time in a minute, but what I'm going to introduce next when we will meet in the right time is that when electron is developing in Bohr's model, it accumulates action. So along the trajectory, it accumulates action. And it must accumulate it in the integer fractions. So as long as something moves, the amount of action changes. And then the wave of something, it will be periodic function with action in the argument, like cosine of action. Okay? Enough. Probably you need to run to other things. I will stay here a little longer if there are some questions. My favorite slide.
I still want to go.